Good day everyone. When we think of linear algebra, we often picture abstract matrices and dry calculations. But today, we want to show you how these mathematical tools apply directly to real-life problems, specifically in sports nutrition planning. As we can see from the data on the slide, different foods offer variety of amounts of macronutrients. For instance, chicken breast is highly packed with protein, white rice is an excellent source of carbohydrates, and avocado provides us with healthy fats. So our goal is to determine the exact amount of each food required to meet an athlete's precise daily nutritional targets, which are 65 grams of protein. The athlete needs 90 grams of carbohydrates and 20 grams of fat. To achieve this, we will construct a system of linear equations and solve it using the Gauss elimination method, transforming our data into row echelon form to find the perfect dietary balance. Moving on to the purpose of our study, first we want to apply core linear algebra concepts to solve a practical, real-world sports nutrition problem. Secondly, we aim to determine the exact serving amounts of chicken breast, white rice, and avocado needed to hit our athletes' daily macronutrient targets perfectly. And finally, we want to demonstrate how the Gauss elimination method serves as a highly effective, structured approach to solving system of linear equations in everyday scenarios.
From the equation, we got protein 30x plus 3y plus 2z equal to 66. Carbohydrates, we get 28y plus 9z equals to 90. Fat, 2x plus 15z equals to 20. We conclude that and we got the augmented matrix. To solve it, first, we swap row 1 and row 3 to obtain a smaller leading coefficient. Then, we create a leading one by dividing row 1 with 2 and insert it into row 1. Then, we eliminate the first column by multiply row 1 and make row 3 subtract with row 1 as shown. Then, we create a second leading one, which we divide row 2 with 28 and we insert into row 2. Then we eliminate the second column where we subtract row 3 minus 3 times row 2 and we insert into row 3. Then we want to create a third leading one, which also will be the ref in the end. So row 3 will be multiplied by negative 28 over 6,271 and we insert it into row 3. Now, from the ref that we got, we use back substitution from row 3. We get z equals to 6,822 over 6,271, which z we will get 1.088. Now, using back substitution again from row 2, we want to find the value of y. We insert the value of z into the row 2. So, y plus 9 over 28, z equals to 45 over 14. So, if we substitute the value z, y we will get 2.864. Now, using the back substitution again from row 1, we can get the value of x, where we substitute the value z into the row 1. Okay. Then we substitute the z value into the row 1. Then we will get x equals to 1.84.
Now that we have successfully applied Gauss-Jordan elimination to our matrix, we get our final value of x equal to 2, y equals to 3, z equals to 1. But what does this exactly mean in the real world? Because our initial variables were measured 100 grams per servings. This tells us that to hit their exact fitness goals, our athletes need to eat precisely 200 grams of chicken breast, 300 grams of white rice, and 100 grams of avocado. By eating this exact combination, they will consume exactly 66 grams of protein, 90 grams of carbs, and 20 grams of fat. However, while math here is perfect, applying linear algebra to real-world nutrition comes with a few interesting limitations that are worth discussing. First, the constraint of reality. In math, system of equations can sometimes give you negative number of fractions. In our case, if our targets required a negative amount of chicken breast or eating a 0.005 grams of an avocado, it wouldn't be practically possible. Second, variable limitation. We only look at 3 food to solve these 3 targets, creating a perfect 3 times 3 matrix. But in real life, a person's diet consists of dozens of different foods. For an example, if we add broccoli, eggs, or protein shake to this meal, it would end up with more variable than equation, resulting in an undetermined system with infinite possible meal combinations. To solve those massive real-world nutrition problems, diet apps actually use advanced linear programming, an extension of the matrix algebra we learned in class.
To wrap everything up, our project has successfully demonstrated how the abstract concept of MAT263 apply directly to a practical real-world sport nutrition problem. By taking an athlete's daily micronutrition requirements, specifically 66 grams of protein, 90 grams of carbohydrate, and 20 grams of fat, and translating them into a system of linear equation, we completely eliminate guesswork. We prove that nutrition planning can be approached as a structured, flawless mathematical puzzle. Through the Gauss elimination method, we construct an outcome matrix using the nutritional profile of chicken breast, white rice, and avocado. By applying elementary row operation to reduce this matrix into row echelon form, we calculate the exact optimized serving size need to hit our target perfectly. Ultimately, this case study highlights the immense value of linear algebra beyond the classroom. While we often view matrices as theoretical exercise, they are highly powerful tools for real-world resource allocation. Whether we are balancing data constraint in technology or balancing nutrient for elite athlete performance, linear algebra provides the perfect framework for finding clarity among multiple variables. Before we close, our group would like to express our sincere gratitude to our lecturer and our team members for their dedicated collaboration. We would also like to note that all external asset and data source used have been formally cited in the reference slide immediately following this conclusion. Thank you so much for your time and thank you for watching our presentation.